Question 2. Benzene diazonium chloride decomposed in water as shown in the following equation. So it will react with water, form phenols, nitrogen gas and HCl. This is the one that we can collect from the experiment. And a solution of 0.075 mole per dm cube of benzene diazonium chloride decomposed at constant temperature at 50 degrees C, and the volume of nitrogen is recorded for every 5 minutes for 45 minutes. Means the total time is 45 minutes and we use a 5 minutes interval. So we record the volume 5 minutes interval. Means every 5 minutes we read one time until 45 minutes. Then we get the total volume of nitrogen gas that collects. Part A. Draw a label diagram to show how the apparatus could be set up to carry out this experiment. First, you have to consider the statement that given here, because it says that constant temperature of 50 degrees C. So we must use the thermostatically controlled water bath. Means we use the thermostat, control the temperatures of the water, make sure it's always 50 degrees C. This is the first thing, because we want the constant temperature, and this is the one that we can control. I mean the temperature. And how we collect the gas, because nitrogen gas will produce. So we must make sure the setup is no leakage and is able to transfer the gas to the gas collector. So let's say now we put the benzene diazonium chloride with water into this water bath. So this benzene diazonium chloride will react with water and form nitrogen gas. Nitrogen gas, then it will get out and it will transfer to this gas strange. So the gas strange here is to let us know what is the volume of nitrogens that produced from time to time. So this is a setup that you need to draw. So this is for mine. You can have your own drawing if you want. For part B, use this method, means the gas collection method. So we get this graph in the figure 2.1, something like this. So this is the initial graph. So this is from the question, this one. So using the 0.07, the initial concentration, 0.057 mole per dm cube benzene diazonium chloride. Okay, after that we will discuss this one later, one by one. Okay, part 1. On this figure 2.1, draw a tangent to the curve at t equal to 0 minutes. Calculate the initial rate of the reaction. The unit is cm cube per minute. So this one is minute and this is a cm cube. So we no need to do extra conversion. So we just use delta y over delta x. So we can get the rate of reaction. Okay, means we calculate the gradient. First we draw the tangent like this. Make sure the tangent is from the origin here, and make sure the graph here, the initial graph, get the original curve able to show, and make sure this the line is at least 5 minutes, right? So this is the requirements. You can actually get all the details from the mark scheme. It's something like this. So therefore, we use the delta y over delta x. You can use one coordinate in the line, in this line. So use one coordinate and calculate delta y over delta x. So for mine, I get around 6.6. So you can have your own values. Part 2. Explain why initial rate of reaction is calculated at t equal to 0 rather than dividing the total volume of gas produced by the total time that taken. This is not good, because as you can see from these graphs, right? So it's actually at different time, it has different so-called rate, means at different point the gradient is actually different. All these gradient actually different, so means it's going to have different rate of reactions at different time. So therefore it's not really good to get the initial rate using the average value. So that's why, okay, this is the answer from Mark scheme. So the total volume of gas produced divided by the time taken is the mean rate. So we don't want the mean rate. Okay, we want the initial rate, which is the fastest one. Actually, in another way, you can say that because different time will have different rates. Means because at different time, let's say 5 minutes, 10 minutes, 15 minutes, it's going to have different rates because gradient different. Part 3. Describe how the curve in this 2.1 would be different if at all, if the atmospheric pressure increases, all other conditions stay the same. Means temperature same, so others like concentration same. Because it's this curve, right, is the gas collection, is the volume of nitrogen, so it's about the formation of gas, and gas is affected by the combined gas law. So we can easily relate to this combined gas law. nRT now is a constant, temperature is constant, so this nR also constant. So when we increase the pressure, then the volumes is going to decrease lah. Right, so to remain the constant. So therefore we know that the volume that collected will be lower. So the curve would be lower than the initial graphs. Okay, this is for sure. For part 4, on the figure 2.1, draw a second curve to show the graph produced if the same volume of 0.375 mole per dm cube of benzene diazonium chloride decomposed at 50 degrees C. So means now this concentration is half of the initial concentration. Means it's going to produce lesser. Means when it reach 45 minutes, the volume of nitrogens that produce must be halved. Okay, because at that time already decomposed. Right. So and because concentration now is lower, the rate is going to be lower because the numbers of particles is lesser for the same volume of the solution. So we know that it should be something like this. We just draw one. Okay, make sure it's below this initial curve, and make sure this one is less steep than the initial graph. And another point is you must make sure this and this volume on the second curve is half of this volume, because concentration used is half. When all decompose, then the volumes that produce should be halved. Right, so okay, so now part C. Another student investigates the effect of changing the concentration of benzene diazonium chloride at 50 degrees C. He measured the time taken to collect 0.015 dm cube of nitrogen and calculates the rates of nitrogen productions. Okay, by dividing 0.015 by time taken. So this is the one that you should do. So you just use this one and fill up the tables. So first one, let's say 0.5 over 21, so you get this. 0.4 over 33, you get this, and you do the rest. Make sure it's 3SF. So we're going to use this one, the rates, compared with the concentrations. We use the easier one. Let's say when the concentration now is double, let's say from 0.1 mole per dm cube to 0.2 mole per dm cube, the rate of the nitrogen production is actually double. So 1.23 to 2.34. So it's almost double. So we know that the order of this reactant is the first order, because concentration double, rate doubles means it's the first order. Okay, part 2, this is what we discussed just now. The reaction is first order, okay, which obey the following rate equation. So this is a rate equation. This benzene diazonium chloride is first order. Explain how the data in 2.1 support this statement. So I told you just now already. You just try to use 1 or 2 sets and compare. So let's say now we compare 0.1 and 0.2. When the concentration is double, then the rate increase from this to this, means it's also double. So we know that is first order. This is how you explain. Part 3. State the dependence variable in this investigation. Dependence means it depends on the change. What is the change actually? The change is the concentration. When we change concentration, what is the time? What is the items, or what is the things that change, or the things that follow? Is actually the time. As you can see, when the concentration that used is higher, let's say 0.5, the time taken is actually shorter, right? When concentration is lower, the time taken is longer. So means the dependence variable, it must be the time that taken to collect the gas, right? Because it's based on the concentration that used. So this is quite clear. The answer is time taken to collect 0.015 dm cube of nitrogen. Okay, now next part. Part 4. The student want to perform similar experiment using 0.2 mole per dm cube of this benzene diazonium chloride. Describe how the student should make a standard solution of 100 cm cube of 0.2 mole per dm cube of the solution from 0.5 mole per dm cube of the benzene diazonium chloride solution. So this one is actually a dilution. We use a more concentrated solution to prepare the standard solution. So you just need to use M1V1 equal to M2V2. M2V2 is the concentration. Okay, this is what we need to prepare, 0.2. Volume that used is 100. V2 is 100. The initial concentration is 0.5, so it's N1. So this is a volume that need to take. So after you calculate, you should get 40. So it means we need to get 40 cm cube from 0.5 mole per dm cube solution. So this is the one that you must put in the answers. Means when you try to list out the steps, you must put these values. Okay, so let's start. Because it's 40 cm cube, it's better for us to use burette rather than the pipette. Because pipette sometimes we try to take a fixed value or fixed volume like 10 cm cube, 25 cm cube. So when it's 40 cm cube, so we can use burette. So use 50 cm cube burette to take or measure 40 cm cube of 0.5 mole per dm cube benzene diazonium chloride solution, and introduce or pour it into the 100 cm cube volumetric flask. So we must use 100 cm cube volumetric flask because it's already here. After that, we need to top up the solutions to the calibration mark. Means we add the distilled water to the flask. Let this water fill up until the calibration mark. So means in the volumetric flask, normally on the neck it has one calibration mark. So we just fill up the distilled water until it reaches this mark. After that, we put the stopper and invert shake the flask. Why? Because we want to homogenize the solution. Invert and shake the flask to homogenize the solution. So this is the full preparations of the standard solution. Part 5. Explain why part 4 must carry out at temperature below 5 degrees C. This one is very easy because benzene diazonium chloride is temperature sensitive. It will decompose at higher temperature. So we need to make sure it's always below 10. Actually below 5 lah. In this question is below 5. Okay, to make sure the concentration does not change. Why? Because the benzene diazonium chloride will decompose when warm. Means when more than 5 degrees C or 10 degrees C. Huh? So this one, part D. Benzene diazonium chloride is used in the manufacturing of the dyes. So a student prepare a sample of a dye using reaction scheme shown in this 2.2. So this is how to prepare the dye. We start from phenylamine, this one, and let this phenylamine reacts with the sodium nitrite with HCl below 5 degrees C. Then this phenylamine will convert or will form benzene diazonium chloride, this one. After that, we use the excess phenylamine, this one again, this one. We use the excess phenylamine to react with the benzene diazonium chloride that form. Means it's something like this. This is the phenylamine, and this one will react with the benzene diazonium chloride. Means the benzene ring here, this one, because this one is electron donating group, so it will direct 246. So the benzene diazonium chloride will bond to this carbon 4. So this one, the benzene ring will form new bonding with this N. So pi bonds break. So this electron move to the nitrogens, and it will get the pair of electrons, and therefore it will form this dye. So this, for your information, this we call azo link. So azo dye in there is going to have the azo link. Okay, so I hope you understand what I told you just now. Okay, so in step 1, phenylamine, this one, so it's converted to this benzene diazonium chloride. Step 2, then the benzene diazonium chloride react with the phenylamine, produce the solid dye, which is this one, right? Then this mixture is need to be filtered. Normally in the lab we do the filtrations something like this lah. So we use the filter paper and we just pour the mixture, means the solutions with the dye, the solids, and pour on the filter paper and let it get down, means let it undergo filtration. Then we will get this solid dye, means the residue on the this filter paper. Okay, so this one we'll discuss again later. Now, part 1, the student final yield was 52%. So means after this reaction finish, the student filter the dye, and after that dried it. So eventually he just obtained 52%. So it's not about 90 or 100%, but now it's just 52% yield. And there had not spilled any reagent or products. Suggest 2 reasons why student yield was lower than 100%. Why cannot get 100%? And assume no error made in the measurement of any substance. Means this one is about weighing. So the mass or what. So the main reason is actually the benzene diazonium chloride itself. Because when the benzene diazonium chloride is formed, And before it react with the phenylamine, I mean this one, before this one is benzene diazonium chloride, before it react with phenylamine, it might decompose because the temperature sometimes is not below 5 degrees C. In the step 2, it's never mentioned below 5 degrees C. So therefore, what we know is the benzene diazonium chloride is temperature sensitive, so it can decompose and form the phenol and nitrogens anytime. So when the benzene diazonium chloride decompose, getting lesser, of course the dye also will form lesser. So this is the first reason. Some of the benzene diazonium chloride decomposed. Second reason is this. So this answer all in the marking scheme. I just try to explain why. Okay, reason 2 is what? Some dye is left in the filter. Let's say now after the filtration, so we get the residues from the filter paper, but you have to understand some of the dye will stick on the filter paper, on the apparatus, and it's hard to take it out. So therefore, it's going to have some mass loss during the filtration. So this is the reason. Or you can say that because the dye somehow it can dissolve in water, so during the filtration it cannot totally we cannot totally get the solids, means the solid dyes. Part 2. Explain why the solid dye should be dry before accessing the melting point. This is very easy. If let's say in the solid dye it has water, so the water will affect the melting point. So it's not the pure or the standard melting point for the solid. So the presence of water in the solid will affect the melting point. Okay, and this one, okay, this is the reason. Okay, why we want to dry the solid? Another reason you can put is to increase the accuracy in the measurement. If let's say now is water free, means no water, so the melting point is more accurate. So that's why we want to do this. Okay, so that's all. Thank you.